Okay, so we are Team States, and this is the final design review for our product, ScubaBot. I will first go into the introduction and overview of the product. So just to go over the problem, in an underwater setting, research or system maintenance requires frequent ascension of divers for task completion. Scuba diving is necessary in these working and research settings, and the researchers or workers themselves are limited in their ability to complete their work underwater due to the inability to ascend or descend frequently. So this limited frequency of ascension or descension enables tools or equipment to be carried back and forth from depth to surface, and it also just enables divers to restore oxygen often. So our proposed solution is an autonomous underwater robot that stays at a certain distance within the diver's location. Our solution addresses these limitations by diving to a set point within the diver's location, resurfacing after loading or unloading tools, and in the process, it can deliver oxygen as needed. So the subset of the overall problem we are addressing helps divers transport equipment and materials from depth to the surface. Our solution allows a single worker to perform complex or numerous tasks, since a wider array of tools are delivered and mobility underwater is increased. So just a quick overview of the capabilities of our model. It can firstly drive to a set point within the diver's location, and this benefit is that it stays safely within a set proximity of the diver. Second, it can navigate underwater autonomously, and this aids the diver by increasing mobility underwater and also just reduces the need for the diver to interfere or manage the actual robot. Third, it can ascend to the surface and return to the desired depth as necessary. So again, it removes the diver's need for them themselves to ascend or descend frequently. Fourth, it can carry equipment, so it increases the range of work that can be performed by carrying more supplies or oxygen than the diver themselves. So quickly, just to go over the product scope, our robot allows for safer diving practices by completely eliminating the need for frequent resurfacing, in part by the diver. So in addition, it increases efficiency in work. The robot's behavior includes steering, swimming, and carrying, and that would be just whatever oxygen or hardware is carried. So in terms of the ECEs, past simulations demonstrate the ability to navigate autonomously and stay at a set distance from the diver. For the ME side, Solidworks analyses address the current flow and pressure considerations that are present underwater. So some key terms from our element definition. The intended practice of our model is to transport equipment or oxygen to and from the surface to the diver and back to the surface. It allows for safer and more efficient diving practices by eliminating the need for frequent resurfacing. It is structured as a waterproof frame to protect the hardware, motors, battery airtake, and valves inside with properly positioned rudders for navigation. And the intended effects are for goods to be transported to and from the diver to the surface with minimal diver assistance or interference. Some side effects, however, do include interrupting the natural environment, requiring manual assistance from the diver, or colliding with underwater environment or losing equipment. So a quick overview of the actual robot. As we discussed before, the capability to navigate underwater autonomously was designed in our part. For the MEs, it's the servo motor and thruster mounting, and for the ECEs, it's simulations to prove path taking abilities. The capability to carry equipment on our part, for the MEs, the cut was made to form storage compartment and doors designed to secure whatever tools or tank is inside. And third, its ability to increase efficiency of diving by reducing the number of resurfacing is shown by a comparison of time simulations of divers with and without the robot. So quick solution overview. So through the simulations, the autonomous robot is proven to traverse the fluid environment successfully. Simulations prove that it can safely navigate underwater in the presence of obstacles and stay a distance of 3.8 meters within the robot's length. And SolidWorks analyses show that it could withstand the pressure underwater and the current flow forces that are present in the underwater environment. So in essence, the problem was solved by implementing an automated system that submerges quickly to the diver's depth and travels safely underwater while carrying tools and oxygen. So now I will go into the mechanical engineering contributions. So my first task at the beginning of the quarter was to assemble the actual model. I continued on with that task in terms of the manufacturing process. So I will briefly describe the body components in terms of how they would be manufactured. So the body is composed, which is the main part of it, is composed of the nose, the front hole, the back hole, the storage compartment area, and the tail. So these can be described as being formed by rolled alloy steel plates, particularly for the front and back hole, given that these are curved into the desired 12-inch radial curvature. Next, the little other component on top of it is a casted tower, and this is casted due to its unique geometry. So the steering for the actual model itself could be composed of casted aluminum rudders. There are actually 4 of them right now. You can probably just only see the 2 vertically oriented rudders at the end. And again, these are casted due to their unique geometry. There's a thruster unit at the end to provide propelling power. And in the interior of the tail section, there are 4 servo motors to power the rudders. Other outside components include 2 aluminum fins, and these are placed on top of the tower. These do not rotate, these are there for stability. The storage compartment doors, which secure any tools or oxygen tank that can be stored within the storage compartment, and the access hatch placed in the front hole. And the access hatch just gives access to whatever components are in the interior, and these would be the battery of valves, the 4 valves, and the air tank. And the rotation of the rudders are allowed to enable ECEs to perform simulations, and that's just part of the navigation or steering component. So as I mentioned before, my task was to realize the manufacturing process. So as I said, to form the front and back hole sections, alloy steel plates are rolled into the desired semicircles with a radial value of 12 inches. And you can see that in the image on the right. And the nose and tail are similarly rolled, except that the curvature of the nose and tail sharpens accordingly to create its endpoint. As you saw in the previous image, the tail sharpens off into a smaller radial value, and the nose curves off to form a more circular point. And in a typical submarine process, these sections are actually placed around a wooden hole template. And the wooden hole template serves as stability to hold the pieces together while these are welded together. Steel plates are welded together. And we chose a wooden template of teak, given that it has the highest heat capacity, so it is able to withstand heat the most. So curved pieces we placed on the wooden hole and welded together. And once the outer surface is completely welded and ready to cool and cooled off, we do need circular steel plates to mark the insides of them to separate into the different sections. And this would be the different sections between the nose and the front hole and the back hole, the walls to secure the storage compartment, and that moves on into the tail area. So once the outer surface is complete, steel plates are embedded and, in our case, welded into the interior to mark the different sections. And external components, such as the tower, fins, and rudders, they are just casted to produce correct geometry. The fins and rudders actually are made of aluminum, so it'd be casted similarly in that process. So moving on to the model subsystem, my latest task was to mount the servo motors. So the first adjustment that I made was to remove the excess arm length of the servo motors and replace it with a more fitting circular base for that. And each one was protected by an aluminum casing, and you can see that in the image. These are represented in blue. So each aluminum casing has protruding tabs, and these are screwed onto each mounting base. So the mounting base are for them. They just protrude from the entry hole, so where the rudders would fit in at the end. And by screwing it on and by using the mounting pole as well to be screwed on, the mounting directs all rotational power to the rudders, meaning that the servo motors are secured and they are attached to the rudders individually. So whatever rotational power that the servo motor has would be directed fully into the rudders. So rudders are able to rotate individually to increase their freedom in navigation. And as I had mentioned before, I had mentioned that the rotors are free to rotate individually, and this is just so that the ECEs could use their rotational values for their own simulations.
A ballast tank subsystem consists of two ballast tanks. The nose acts as the front ballast tank, while the back hole acts as the rear ballast tank. To increase buoyancy, air is injected through the side of the ballast tank, and water exits through a complementary hole located at the bottom, or in the case of the rear ballast tank, multiple small holes. These holes were positioned to not intersect any weld lines, as this would compromise the precision of the holes. To decrease buoyancy, air is released from the top, and water is then allowed to enter through the bottom as a result. In order for this system to work, 4 electrically actuated valves are used. 2 of these valves are mounted to the sides of the ballast tanks and are connected to the air tank. These valves are then open to inject air, while the 2 valves mounted through the walls of the ballast tank are opened to release air. The valves, air tank, and battery are housed in the mid-compartment. In order to access these components, the mid-compartment has an access hatch, which was designed to have interference in order to help prevent water from entering. The mid-compartment also contains a wire channel, which is used to run wires from the battery to the thruster and servo motors located at the tail. In order to prevent the battery and air tank from moving, 1-inch thick rectangles of metal were welded to the bottom of the body in order to restrain the battery and the air tank. The locations of these restrainers were determined by the dimensions of the air tank and battery. This design allows the battery and the air tank to be easily removable and replaceable, while also preventing them from rolling and sliding.
Preliminary static analyses indicated that at our given maximum depth of 100 meters below sea level, our model would not fail, yet it would only correlate to a factor of safety of 1.3. However, based on our research, for your typical submarine or autonomous underwater vehicle, AUV for short, a factor of safety of 1.5 is standard. That being said, at this point, there was still a great deal of work remaining to put into the model, such as adding the internal component mounts and housings, as well as the ballast tank system. At this point, though, our model seems strong enough to go ahead with these other alterations and come back to the static analysis later to make sure we achieve a factor of safety greater than 1.5. Once the model was updated, another static analysis was required. However, at this point, our model had much more complex geometries, making the analysis more complicated to run. Various simplifications of the submarine were required in order to produce a model that could mesh and solve within a reasonable amount of time. First, all parts besides the main body of the robot were suppressed, as the main body is the only component under any significant forces. Next, the nose was suppressed as it is part of the ballast system and therefore not closed off from the surrounding water. To reiterate, the way our buoyancy and leveling system works is that in each of the ballast tanks, a hole at the bottom is always open. As such, there is no pressure difference inside and outside the nose compartment, as water is able to flood each compartment until the pressure equalizes as the air inside is compressed. The air being controlled by the valves connected to the air supply. The same goes for the other ballast tank, except that small holes were replaced with 2 large holes in the side to aid in meshing. All small valve holes remaining were also suppressed, as these will be sealed and precisely controlled. Lastly, the thruster system and fins all have components that must extend from the inside to the outside of the body shell. The final alteration was the filling of the access hatch and any holes created for the mounting of the fins and thruster unit, as the sealing of these holes will be outsourced. With the geometric simplifications complete, the model was then prepared for analysis. Fixtures were applied to the walls of the center ballast tank as no significant forces are acting on them. The pressure force, 160 psi at 100 meters below sea level, was then applied to the outside surface of the body, the inside walls of the storage compartment, and the inside walls of the center ballast tank. Finally, mesh controls were added to refine the mesh in areas of difficult and small geometry, mainly the fillets and ballast tank holes. At this point, we ran a second analysis which verified a very similar factor of safety of 1.3. From there, the thickness of the 3 selected circular walls, well, I guess they're half circles because of the section view, but the thickness of those selected walls shown in the upper figure was doubled and fillets were added where these walls meet the outside shell of the body. As you can see in the lower figure that shows the stress plot, for which I feel it's important to note that the displacement is shown exaggerated by a factor of 75. It shows that we were able to achieve a factor of safety easily above 1.5. This also demonstrates visually the areas of stress concentration and why the extra thickness and fillets help. In order to determine the propulsion system for a submarine, computational fluid dynamics was applied to the Solidworks assembly in order to quantify the drag force the robot must overcome while traveling underwater. Naturally, water was selected as the fluid for the analysis, and the pressure was input to the pressure at the robot's maximum depth, once again 160 psi. It is not shown in the figure, but the only other modification to the default analysis settings was a shrinking of the computational domain. While it still encapsulates the entire robot, of course, the volume was reduced dramatically in order to speed up analysis time. Shown in the image, the green lines correspond to various streamlines, and they take the expected paths around the submarine. You can also see the concentration of force where we would expect it to be, the center of the nose and the little red area. Typical autonomous underwater vehicles in this size range usually travel at speeds of 1 to 4 knots, or about 1/2 to 2 meters per second. So 4 different flow analyses were conducted at intervals of 1 knot, providing the data for the table shown. From this table, we can surmise that we must be able to provide at least 60 pounds force of thrust to the AUV at certain moments, but to conserve battery life, we concluded that a sustained thrust of approximately 15 pounds is appropriate for normal operating conditions at 2 knots velocity. From here, we found an appropriate thruster system, the H106 electric thruster by Interspace Core, to use with our assembly. The specifications of the thruster are omitted in this documentation, are admitted in this presentation, as the documentation is far too expansive to cover on a slideshow presentation, but it is all included in the final design review. This thruster outputs sensor information in the form of rotational speed, thrust force, temperature, current, and voltages. It is also able to take commands from the main controller in velocity or torque mode, which it makes it very convenient for simple integration to a vehicle stability system. Furthermore, referencing once again the table available in the final design review, but not here, the power supply to the thruster system must be able to exceed 1500 watts and sustain 300 watts at 100 volts for multiple hours. With these requirements, a battery pack was found to satisfy the robot's demands. The Sub-C-Tech 260 millimeter high voltage battery. Similarly to the thruster unit, the battery has comprehensive documentation included in the final design review, but left out here.
One of our initial main deliverables was a Webots simulation that showcased our robot's motion capabilities in a fluid environment. Since we had limited experience using Webots, we knew we would need a lot of time to experiment and learn how to work with simulated fluids. Therefore, one of our first priorities was to create a preliminary shell model of our robot that we could import into Webots and use to learn more about Webots' capabilities. The main thing we learned was that fluid nodes do not actually simulate particles filling up a volume. Instead, they simply add a drag force to any solid that moves through it. This proved to be a major problem for a robot since the ballast tanks cannot operate unless they can be filled and emptied. Nevertheless, we moved on while testing out alternative solutions. We created separate worlds containing only one of the actuated components in order to make sure we could properly integrate our controller using rotational motor and propeller nodes. With a collaborative joint effort from both the EE and ME sides, we were able to successfully actuate these components. In the end, however, due to the limited capabilities of Webots regarding fluid environments, we decided to direct our efforts elsewhere. Instead of finalizing a simulation that required us to make many assumptions and thus limit the value provided in regards to demonstrating motion capabilities, we thought that our very limited time would best be spent on more worthwhile work instead. Here you can see as far as we got in simulating our motion dynamics before we decided to scrap this work. Neutral buoyancy is assumed and forcefully applied, making the simulation very trivial. As mentioned before, we could not use Webots to simulate the buoyancy control capability of our ballast tanks. Instead, we performed some calculations to show that the possible buoyant forces provided are capable of submerging and surfacing our robot. We didn't have enough time to design a buoyancy controller, but the ideal situation is that the robot will surface when the tanks are completely empty, and it will achieve neutral buoyancy when the tanks are completely full. This would completely remove the need for a buoyancy controller and make things much easier. Future work would be to make these changes and verify their effectiveness. Since our robot operates fully submerged in water, we had to consider how to ensure it is waterproof. We decided that we can use a combination of rubber U-cups and labyrinth seals to create the necessary watertight seals for the holes in the hull, created for the fins, valves, and propeller unit. We also designed the access hatch with a rubber gasket in mind, so as to work even better in high-pressure environments.
Be talking about the EC contributions to this robotic project for Team States. Next slide, please. So first, we're going to talk about the mathematical formulation that we came up with. And here we formulated the state space, action space, and system dynamics of our robotic system and its motion. So here we actually had two major iterations of our mathematical formulation. And so here I'm going to talk about the first one. And here we have our original state space. And here you can see we have, I think, 18 variables total. So we had X, Y, Z, alpha, beta, gamma, R, FL, and FR, and the derivative of each of those. And so to talk a little bit about each part, we have X, Y, and Z, which are the coordinates along the X, Y, and Z axis respectively. And these coordinates are defined in relation to the start, so the origin, the start position, wherever the boat is on the surface, as well as the diver location. X, Y, and Z would be X max, Y max, and negative Z max for that. So it's almost like traversing across a cube. And then we have the angles alpha for azimuth, beta for elevation, and gamma for tilt. And they're shown here in this little diagram on the right, the kind of relationship between them. So there are various orientation angles along the X, Y, and Z planes and axes. And then we have the rudder angle R, which is the angle with respect to the robot's longitudinal axis of the rudder. And here we have right being positive. So the positive value is going up to pi over 4, and the negative value is going all the way down to negative pi over 4. And then we had two fins. So we have the left fin angle and the right fin angle, or two fin angles. And the angle is defined with respect to the transverse axis. And so because there are two measures for this, we have up being positive, not one of the sides. And here we have pi over 4 being the maximum positive value and negative pi over 4 being the maximum negative value for each of these. And each of these derivatives are of the same type of quantities, and they describe the change in each of their respective quantities. And so talking about the original action space, we had a propeller force PF, which represented a force applied by the propeller to move the system. And then we had the derivatives of the rudder angle change as well as the fin angle change, and for the left and right fin angle changes. And these were all defined as the second derivatives of the rudder angle and fin angles respectively. And because that helped define the we thought that would help define the movement of our system at the time. Next slide, please. And here we have the original system dynamics. And so here we have all the variables with as described earlier, and as well as their changes and the changes in their derivatives. And so things to note here are the changes in the derivatives for x, y, and z is defined. You can see here they have the terms like they have cosine beta, cosine alpha for the change in dx over dt, and cosine beta sine alpha there. And that's defined by the propeller force going in each of those directions. So we have the alpha, beta, and gamma angles, and they're multiplied by the propeller force based on a rotational matrix that I'll go into a little later. And that defined the component of the acceleration or force going in each direction. And then later you can see the change in alpha, beta, and gamma. And here we have certain simplifications made, such as this constant 0.07. And this is a constant that we originally got from approximations cited from research that would help define this change. And that's cited later in our FDR, and I'll talk a little bit more about that later. And yeah, that's the major things to note. And so here we have the updated state space and the updated action space. And as you can see here, our updated state space is a lot smaller. Here we went from, I think, 18 or so variables to 8 variables in our state space. We just have the x, y, and z, the derivatives of each of those, and then the angles, alpha, beta, and gamma, none of the derivatives of those. And the x, y, and z are defined exactly the same. Azimuth is also defined exactly the same. Azimuth, elevation, tilt are all defined exactly the same. And then with values ranging from 0 to 2 pi for each of those. And then the derivatives of x, y, and z are also the same. And in our updated action space, we got rid of the derivatives of the rudder angle and the fin angles. And we have the same, so we took the same base values for rudder angle, fin angle, and the fin angles we moved them to the action space. And then we changed propeller force to propeller acceleration to represent the acceleration value applied by the propeller. Next slide, please. And here we have our updated system dynamics. And so as you can see, there are a lot fewer equations because there's a lot less state variables to update. I guess the major thing to talk about here is the inclusion of the rotation matrix and specifically the components of pitch, roll, and yaw. And these are all components describing 3D rotation orientation of a system, in our case, our robot. And here, each of those components is defined here in a matrix. And once you combine them all by multiplying them, you create a single rotation matrix. And then what we did to get the components of acceleration, or to get the components of acceleration to derive the change in each direction, is we took the propeller acceleration value, which was just a scalar value, or no, not a scalar value. It has 3 components in x, y, and z. And once you kind of match the dimensions of that with this rotation matrix, you create this matrix which we called R star, or it's a 3, and it creates a 3 by 1. And once you multiply this by each of the propeller accelerations, but once that's the values of R star are the rotation values multiplied by the propeller accelerations, and then these give you updates in each specific direction, x, y, and z, that the robot is going to be moving in. And so that abstraction is shown here in the update equations for the x, y, and z values respectively. And then down here you can see the update values for alpha, beta, and gamma. We changed the constant change from 0.07 to 0.2, and this is something that we found from further outside research, because this is something that we had no previous experience with. And so that research is again cited in our FDR, and I think we'll be talking about a little later too. Next slide, please. And so here are just some tests to show there's just tests showing how we kind of verified our system dynamics did make sense. We set a few different trajectories and ran very simple analytical simulations in Python to see if the system dynamics we defined would lead to the expected behavior and expected movement. And as you can see, some of these tests were very simple, like test 6, which is just moving directly vertically, and then test 1, which is moving kind of in a diagonal downward fashion. And some were a little bit more complicated, like test 3, which is kind of like moving like a spiral. But each of these matched with what we expected to see in the movements. And so this helped us qualitatively kind of analyze and affirm to ourselves that these system dynamics did make sense and did correctly map our system.
So now I'll be talking about the analytical simulation and specifically the features of it, because we weren't able to do numerical simulation in Webots due to limitations in Webots, basically simulating fluid and the physics of it. So we basically had to beef up our analytical simulation a lot to integrate with the body that the mechanical engineers made. So there's a list right here. I'll just go through really quickly. We have the mass of the robot, which is important for determining the acceleration values and the torque based on how the fin and rudders are turning. This leads into the drag force dynamics in the fluid, which is we found torques based on the computational fluid dynamic analysis of our specific robot. We also have LQR control, along with a script to find the optimal Q, which is a hyperparameter of the LQR control that minimizes the area between the waypoints. We add noise in the actuation because obviously what we tell an actuator to do might not be what it actually does in a fluid environment. We also provide sensor and environmental noise because again, in the fluid environment, we want to make this as realistic as possible, not just a simple simulation. And in the fluid environment, there's going to be a lot of noise that might cause the robot to end up in a different position than it expects to based on the pure system dynamics. We clip the acceleration based on the maximum thrust possible from our chosen thruster in a given time step. And similarly, we clip the rudder and fin movement based on the maximum deflection angle that our chosen motor could rotate our fins and rudders by. Like Revanth talked about earlier, we have second order system dynamics, including the velocity of position. Unfortunately, not the velocity of orientation, because tuning 12 variables with LQR was proving infeasible, so we had to reduce it to 9. And we also have obstacle avoidance with the buffer zone because we want our robot to be able to navigate through obstacles and around obstacles to get to the diver or the boat from where it starts. And because of these obstacles, we want some sort of path planning algorithm for the boat to follow or the submarine to follow. And we decided to use A* for that because it wasn't too computationally expensive, given that the maximum direction that we would travel in X, Y, or Z was approximately 200 meters. So when you discretize that by meter, it becomes a maximum 200 by 200 by 200 grid, which is not too hard for A* search to find the best path through. Next slide. So this is a simulation output of A* search. As you can see, the robot is starting at the diver in this scenario and going up to the boat, but it works both ways. And the graph on the right, it's more visible how the search is actually successful. You can see that it's technically not the shortest path because it could take a slightly straighter path. This is because we added buffer zones around the obstacles because the length of the robot is 3.8 meters. And obviously this simulation is only considering a point. So we want to make sure that we have a buffer zone around the obstacles to really ensure that the robot is not hitting these obstacles as it follows the shortest path. We also have LQR, as I described earlier. This slide is taken from Wikipedia, and it's basically describing the finite horizon, discrete time, linear system that we're working on. There's an A and a B matrix, which fully describe the system dynamics. And then we're basically reducing a quadratic cost function given by the Q, R, and N matrices in the second line. The N is noise, so we actually don't worry about this for now. We add it on later because the noise in the situation would be deterministic, but our noise is going to be random because we can't predict the noise that the robot is going to go under while it makes its journey. So we just have a Q and R matrix that we have to tune, and I'll talk about that later. And basically the goal of LQR is to find the optimal cost input, or the optimal input based on the cost and the system dynamics. These are the A and B matrices that we used. It's kind of dense to follow if you just look at it right now, but basically the A matrix is 9 by 9 because you're inputting the current state or the old state, and you're adding that to B times the input. So the input is has 4 degrees of freedom, and the state has 9 degrees of freedom, which is why B is 9 by 4, and A is 9 by 9. So like it said in the previous slide, the new X is going to be A times the old X plus B times the input. And these are the Q and R matrices that we used. This Q is actually the Q that we use for our final simulation, which we'll talk about later. But to find this Q, we were using a script because Q is something that needed to be tuned based on the given problem. So for each path that we analyzed, we would run the script to find the Q that minimized the error between the path that the A-star search generated and the path that the robot ended up taking. And then we would choose the best Q that minimized this error and stick with that. And then in the R matrix, you can see that the first element is way bigger than all the rest. This is because the first element is considering the cost of thrust, which is way more valuable and cost intensive to us than simply turning the fins or the rudders, which is the next three. So these are some simulation outputs of obstacle avoidance, LQR control, noise, everything I talked about earlier. And you can see that you can see immediately that there's something wrong going on. The black path is the A-star search path, and the green path is the path the robot actually took after finding the optimal Q. So you can see it's having trouble first making the sharp right turn, and then subsequently making the sharp left turn around these obstacles to get to the goal point, which is denoted by the green star at the end of the black path. And on the next slide, there's a couple more examples showing how it fails. On the left of the slide, you'll see that it basically goes straight down and just cannot figure out what to do after that point. And on the right is actually catastrophic failure because the robot is going through the obstacle, so it would definitely crash. And that led us to reduce the scope of our problem to remove obstacles while basically beefing up the noise to compensate for that, like Abhi will talk about on the next slide.
Yeah, so this for the final analytical simulation, we have the exact same set of features minus the obstacle avoidance and the shortest path planning, because when we remove the obstacles, we no longer need the shortest path planning. But again, just to recap what Niyant said, the reasons why we removed obstacles was because we wanted to ensure we had a high confidence of success for the product. So we figured that the surface team that would be running this robot would position the robot in such a way that it's only traversing open waters and it doesn't have to worry about obstacles. So it can take a straight path straight to the diver. As a result, we no longer need to avoid obstacles, and it significantly improved our ability to constantly get the robot all the way to the diver within either the length of the robot or just a few meters more. So let's just talk about a couple of trials. So this is the initial trip simulation. So this is from the boat to the diver. And as you can see, it gets to within the length of the robot, which is what we deemed as success, which is 3.8 meters. And we'll talk more about the noise, but this includes noise as well. And the noise here is 2% of the position and 2% of the actuation. And I'm sorry, not 2%, 2% of all the actuation and 0.2 meters of the position and 0.2 radians on the orientation. And this is a simulation for the return trip, similar noise values. And you can see that the graph is a bit wobbly, and that is just it responding to noise. So what I'll go through now is some iterative development and how we increase the noise to kind of find points of failure. And this is just another more close-up graph of the trial that I just showed you before. And again, this is for our final simulation. So this is the one that would go in the final product because it has the highest chance of success when run over and over again. So as you can see, 2% for the thrust, 2% for the rudder, and 2% for the fin noise, and 0.2 meters for the position and 0.2 meters for the orientation. And it's in each direction for the position and for both and for all alpha, beta, gamma, so tilt, elevation, and azimuth for the orientation noise. So this graph here shows same path, but with more noise. So 5% for the thruster, 5% for the rudder, and 5% for the fin, but we kept the position and orientation the same. As you can see, it has been more noisy, and it doesn't get all the way to the diver within 3.8 meters. It is about 10 to 15 meters off, but it is still workable. So next steps would be to fine tune this and get it to be closer to the diver at the end of the simulation or at the end of the path. Then this would be future work past the scope of the project. So then, and the next one here is again 2% for the thruster, rudder, and fin. So this is what was included in the final simulation. But what we did here was we upped the position and the orientation noise. As you can see, it is a bit more noisy. So the position and the orientation affects the behavior much more than the actuation noise, and that's to simulate things like fluid dynamics, external forces, current, stuff like that, as well as mismatched sensor data or just bad sensor data once we actually incorporate sensors. And as you can see, it's really wobbly. And again, it doesn't get all the way to the diver, but again, it's within 10 meters or so. So it's still can be improved and still can be a viable product and withstand this amount of noise. So then the next one here is a combination of the 5% actuation noise and the 0.4 meters in radians for the position and orientation. And again, so it still gets pretty close. And this one's actually better. This one's about 5 meters off or so. And it still shows pretty significantly noisy data, but it's not catastrophic failure. This one again, this is 10% for the actuation, and you can see it goes in a different direction initially, and then caches itself, and then starts going towards the goal state, but it's still getting pushed off and of the path, and but it still catches itself and goes towards the goal state and ends up, I want to say maybe about 5 to 7 meters away again. And this one is 10% for the actuation and 0.5 meters for the position noise and 0.5 radians for the orientation noise. As you can see here, so this is where we saw catastrophic failure. This is when we up the noise to 20% for the thruster, rudder, and fin, and it's a whole meter and a whole radian for the position and the orientation. So this is pretty significant noise. So this would be either really rough waters or terrible sensor data or poor actuation for all our actuators. So it makes sense that it wouldn't get to the goal state or to the diver. And it makes sense that this wouldn't work. But again, this is where we're trying to find points of failure, and this is not our final simulation. Next, I'll talk about this is of the noise values and the position and the position noises, the orientation noises, and then all the actuator noises. So these are all histograms, and this is just to show the distribution, the normal distribution, and how it mostly stayed around negative 0.2 to 0.2 for the position and for the meters. But it did get to about half a meter or a little bit less than half a meter on each end. And so it's important to know that these are for successful trials. So this is for the final simulation. And so this is the standard deviation of 0.2 meters. And so as you can see, it does get pretty high at times, but this is for the simulation that we had high degree of confidence that it would be a workable product and it would be consistent enough to get to the diver and back to the boat often. And so here are more graphs for, this is the orientation noise. Again, 0.2 is the standard deviation in radians for the orientation. And this is for each direction. Both are all azimuth, tilt, and pitch. I'm sorry, azimuth, tilt, and pitch. This is acceleration. These are the fins and rudders. So these ones, as you can see, again, it varies, but it consistently sits around 0.2 to negative 0.2 to 0.2. And again, this is for successful trials. So these are all good values. This is what we can work with. As you can see here, it gets pretty noisy, but it's still clipped at 0.61. This is to make sure that it doesn't get to undefined behavior and it doesn't get to values that the rudder can't actually go to or the fins can't actually go to. It's very noisy here, but again, this is for successful trials. This is what we can actually deal with, and we can have consistently successful behavior with our working product.
So now I'll talk about our conclusion after we've gone through our sensor system, our actuator system, our algorithms, as well as all the work done by the mechanical engineers in their work on the body and the fluid and static analysis. Next slide. So just to reiterate the problem that we're solving, in an underwater setting, research and system maintenance requires frequent descension of divers for task completion, as well as frequent ascension of divers, which can cause air to get caught up in the diver's blood, which has serious health complications. And this is going to limit the amount of work that can be done underwater in any given moment. Coupled with the fact that tools are usually super heavy to bring down for maintenance or research purposes, a robot that could basically deliver these tools back and forth so that the diver could travel lightweight, as well as deliver oxygen back and forth so that the diver can stay down there longer, would really help in lengthening the amount of time that divers can stay underwater with these missions, and be able to basically expand the reach of ocean exploration done by humans. Next slide. So like we discussed, our proposed solution was to build an autonomous underwater robot that could travel to and from the diver. Obviously, the main points that we would need to show and have shown throughout this presentation are that the robot can travel autonomously to and from the diver, that it can withhold pressure as well as the payloads that it'll be under for a typical depth and speed, and basically show that it will allow a single worker to perform numerous tasks more so than he or she would be able to do originally. Next slide. So the project scope initially was to have our robot be an end-to-end solution that was basically left in the water, uses sonar to navigate back and forth, and have a rigid body capable of handling all the pressures that it would be under. We had to reduce the scope throughout the course of our work. And what we're basically delivering on the ECE side of things is a navigation algorithm that is extremely robust to noise, that allows the submarine to autonomously travel back and forth. This, coupled with a buoyancy system that are within the range of our noise, would fully act as the brains of this robot and allow it to traverse the environment well. On the mechanical side of things, we would need analyses to address the current flow and pressure considerations, which are the main mechanical components of the submarine. We need it to be able to turn properly based on the given torques and the fluid dynamic analysis on the body. We would need it to withhold ocean pressures at its depth, and we would need it to be able to withstand the payloads of the tools that it would be carrying. We did not reduce the scope of this that much. Unfortunately, the only thing we were unable to complete in this section was the actual wiring of the internal components. But what we did provide is all the internal components, the prices for them, and the mounting areas for the battery and the wiring and stuff like that. So someone buying our product would not only need the buoyancy control algorithm from the algorithm side of things, but also to complete the wiring on the inside, which would build a fully functioning autonomous submarine that would be able to reduce the amount of resurfacing needed by divers in a research or maintenance capacity, and allow them to have multiple trips of tools and oxygen to extend the time that they could do work underwater. Thank you.